Sorry, my software limits me to 15 minutes of talking. Let's start over with the area of triangles. We're used to the Euclidean area of a triangle being half of the base times the height. But if we use this formula, we get three different answers in hyperbolic and spherical triangle, depending on which side we use as the base. So the two new area formulas are given below, one for spherical triangles and one for hyperbolic triangles. The exterior sum of angles in a triangle is always 360 degrees in Euclidean geometry. But what about spherical and hyperbolic geometry? If the sum of the angles is greater than 360 for the interior, then that adjusts and compensates for the sum of the exterior angles. So those also change. The Pythagorean theorem is not valid for spherical and hyperbolic geometries, at least the way we know it. In fact, in taxicab geometry, which is coming up next, the theorem for the sides of a triangle will just be the sum of its legs, equal to the hypotenuse. Very simple. Here are a couple of interesting links that you can check out that are fun to share. The first one is Poincaré pool, as in billiards table. Let's let this one run the flash. This is a very strange pentagonal pool table because that's a little bit more exciting than a rectangular one. And you can actually change the different shapes if you want. So if you want to go back to a square one, we can do this. And basically, you just click the mouse somewhere inside the pool table to start, and the computer sends the ball, and watch how it acts. It doesn't, oops, I got it in a pocket. How often do you think that will happen? Let's try it again. Start over. Let's pick close to the pocket here. Oh, we thought it was going in, but it didn't quite. So our normal Euclidean pool properties that we're used to aren't quite the same with this. You'd have to learn all new instincts for this game. Here's one where it's an applet that lets you explore the Poincaré disk. This one, you just start drawing lines. There's one. I think I want to draw a triangle, so I'm going to make another one. And then the third one, which I should join these two sides. And there's a Poincaré triangle. You can try anything you want. You can try drawing a line. If I pick a point over here, how many lines through that point can I draw that's parallel to my other line? Well, let's see. Here's one. Here's my point. I wish it would do a point. I could do, oh, it's only let me do one at a time. But just pretend like there's a point here and I can draw any number of lines through it that I want. Hyperbolic tessellations. They're fun to do tessellations on hyperbolic geometric places. Here, this is a Poincaré disk and it's been tessellated using a pentagon. Notice that the sides are sucked in so it looks like hyperbolic that we're used to. And as the as the pentagon is then tessellated and made smaller and attached to the sides, it isn't really smaller, at least it's mussed up with the idea that we're going towards infinity. And so each of those not only is getting smaller like we do in it looks like it's getting smaller, but it's really the same size. It's just we're putting more and more space into it. It's like it's roughly like a hyperbolic doily. Here's another picture where they've tessellated a square. And you can see on the edges how it's getting infinite, and infinity is messing with our picture. Escher made some hyperbolic tessellations. These are some of his famous pictures, the ones with the flying fish. And you can see that he built them up off of a square and then tessellated off of that with the triangles, and he alternates the squares and triangles to actually do a tiling rather than a tessellation. Taxicab geometry is another geometry that is non-Euclidean. We're going to talk about the discrete type of taxicab geometry because there are two types. And this particular geometry works on a lattice of perpendicular lines where there is nothing in the space between the lines. It reminds us of a very nice gridded road system. And so this lends itself to the analogy of driving on the road. If you're in the taxi and you're driving to the bank, you could just drive the 2 blocks and be there. If you're driving to the library, of course, you can't just drive across people's yards, so you'd have to stay on the roads and drive to the library. What is the shortest distance to the library? What if you wanted to drive to McDonald's? Again, remember that a straight line means the shortest distance. So we can drive a straight line to the library, and yet we have to make 2 right turns. Where's the straight line that's the shortest distance to McDonald's? This is connected to my Flash website. I couldn't figure out how to do that here, so we're going to go work with the Flash site. So we want to drive to the library. Pretty radical taxi driver, he needs his muffler fixed. The distance is 4 blocks from where we are. We can't take the shortcut across people's yards or across the non-existent space. We have to go where the roads are, and so it takes us 4 blocks. Now what about McDonald's? How many blocks to get to McDonald's? What is the shortest route? Well, I hope you noticed that there's more than one shortest route. Let's check out some of those routes. There's one. The red route went forward 2 blocks, turn right, go 2 blocks, and McDonald's is on your left. But what about the green, yellow, and blue routes? Are these 4 the only routes to get to McDonald's? How many routes can you find? These are all of equivalent length. They're all the shortest distance, so they're all straight lines in taxicab geometry. So taxicab geometry is one where the first axiom is the one that changes. There's no longer a single straight line between any 2 given points. When we draw polygons in taxicab, sometimes they look the same, like a square and a rectangle, who are already oriented with north, south, and east, west sides. But when we try to draw any kind of a shape that has a slanted or diagonal side, then we have to do the zigzagging to stay on the road. Here's an example of a right triangle. A right triangle with the same congruent sides could look very different. The left side and the bottom side are going to stay the same, but the hypotenuse can be drawn in many different ways. They'll all have the same length, but they may or may not have long sections or zigzags. An equilateral triangle is also going to be zigzagged. This is an example of a symmetrical one, but it could not look symmetrical. The kite and the rhombus and the right trapezoid all end up with these zigzaggy sides where we would think of them as being slanted. What would a circle look like in a taxicab geometry? How could you drive in a circle if all the streets are straight and perpendicular to each other? Well, think of the definition of a circle. It's all points at a given distance from the center. What would a circle with radius 3 look like? I'm going to have you do this for homework, so we won't answer it here. Here's a fun online game to play with your students. It's a taxicab treasure hunt. We're again going to visit another website. This is not mine, but it is fantastic. And here we have a map. The streets that go east and west are named after trees. We have fir, elm, dogwood, chestnut, birch, and ash. The streets that go north and south are 1st, 2nd, 3rd, 4th, 5th, and 6th Avenue. And the point of this game is that I, or you as the teacher, are going to hide a treasure at one of the intersections, and the students are going to try and find it. Here's the interactive one. Now the treasure has been hidden, and we need to select a corner. So let's say it's going to be at the corner of 2nd and Dogwood. How's our guess? Well, it's 6 blocks to our treasure. So what do you want to do next? The red star shows where we chose, and we can figure out what is 6 blocks away. So let's see, if we go over 4 and down 2, we could guess Birch and 6th. Let's try that. 6th Street and Birch. It's 2 blocks to the treasure. Now we have 2 points to determine, and you can go on guessing using the information that's given you to determine where the treasure is. Kids like to do this, and they like to play it over and over. A famous problem, the 3 utilities problem, also comes in with non-Euclidean geometry. If we have 3 houses and they each need to have 3 utility lines taken to them, and we don't allow utility lines to cross in any way, it is impossible in Euclidean geometry to have all 3 utilities go to all 3 houses. However, if we change to a non-Euclidean geometry, like a torus geometry, we can solve this problem. Now, a torus is a math word for something that looks like a donut, something that has a hole in it. If we think of torus geometry as the surface of the donut, then we can solve this problem by having one of the utilities go down through the hole and sneak up on the outside. See where the purple utility sneaks through the hole and comes up on the back side of the pink house. This can also be done with a sheet of paper if you allow your students to punch a hole in the paper, draw a line over to the hole, across the back of the paper, and sneak up on the other side. So it's one way of solving a problem that can't be solved in Euclidean geometry, but it can be solved on a torus.